So today we're going to talk about sections 1.1 to 1.3 in our class, and that's going to involve midsegments, bisectors, concurrent lines, medians, and altitudes of triangles. So as we go through, we're going to just kind of pick and choose some different parts of geometry that have a lot of value to them. And some of the things that we're going to be doing here is you're going to be writing down definitions and doing some examples. So make sure as we're going through, you're writing down all the different things that we're going to be talking about. All right, so first thing, we're going to talk about this thing called midsegments. Okay, so in a triangle, okay, obviously we all know what triangles look like. Okay, that's a pretty simple one right there. Okay, triangles have these things called a midsegment. Now, what is a midsegment? So let me write that down for you. So midsegment is, oops, that's not supposed to be separated like that. Sometimes the computer thinks it knows more than what it is. Okay, it's a segment connecting the midpoints of two sides. Okay, sounds simple enough, so let's just do an example. So over here on this triangle that I'll just call it triangle A, B, C. So a midsegment, as it says, is a segment connecting the midpoints of two sides. So if I call this right here, that spot right there, okay, and if that's a midpoint, and the way you can indicate a midpoint, okay, is you put a little mark on these two portions of that side. Okay, let's call this point D right there. And so this being a midpoint means that AD is the same length as DB. Okay, and then down over here, let's put another point. Call this E. Now that's the middle of BC, so I'm going to put two lines. I put two lines because that indicates that these are both the same. Okay, when I say that, I mean these are both the same, but they're different than these. And so the midsegment would be very simply this blue line that I'm going to then create from here to there. It just connects, okay, the midpoints of two sides. And on the other part, right here, I can do another one. Let's say that's the middle right there. I'll indicate that like this. And if I wanted to, I could draw a midsegment from here to here. And there's also another midsegment that goes from here to here. Okay, because remember it says a segment, okay, connecting the midpoints of two sides. And that's all really a midsegment is. Okay, now, what else does it do for us? Well, there's, based upon that, and you can kind of look at it. If you look at this a little bit, you'll see, okay, it looks kind of natural. How is this line DE, and this line AC related? Or this line right here, whoops, I guess I didn't name this. I should. Let's call this F, this point F right there. So how is this right here related to this? Or this related to this? Okay, and if you're thinking to yourself they look parallel, okay, then that's actually pretty accurate. And so we actually have a theorem. It's called the triangle midsegment theorem. Midsegment, okay, theorem. I'm just going to do a theorem like that. Okay, we'll shrink this out a little bit more. Okay, and what that says is, come on, because it doesn't like, there we go. Okay, and what it says is basically if a segment joins the midpoints of two sides, okay, the segment is parallel to the third side, okay, in half its length. All right, so let me write that down, what I just said. Okay, if a segment joins the midpoints, okay, of two sides, okay, so that means if it's a midsegment, okay, of a triangle, then the segment is parallel to the third side and is half the length. Okay, that seems fairly simple. So for instance, we're looking at my triangle up there. So give me a second, I'm going to move this up just a little bit. Okay, if we can so as we're looking at my triangle ABC, so what that is saying is, one is that every midsegment, so let's say this midsegment right there, okay, and then AC, okay, are parallel. So what I'm going to do is, here's the way you would write that. You would say, hey, DE is parallel, those are the symbols for parallel, to AC. Okay, and what that also is saying is that DE is half the length of AC. Okay, and that's true also for all the other portions. So you could say something like EF is parallel to AB. Okay, you could also say that EF is half the length of AB. Okay, and then knowing that, what would you say the other part would be? Hopefully what you're thinking in your head is that DF would be parallel to BC, and that DF is half the length of BC. Okay, and that's the triangle midsegment theorem. Okay, pretty simple right there. All right, so let's keep moving. So the next part that we're going to talk about are bisectors in triangles. Okay, a bisector. Let's think about that, just that word in itself. What is a bisector? Okay, and I'll write this down for you. Bisectors in triangles. That's what we're going to talk about next. All right, so what the heck does that mean? Well, let's think about that here for a second. Bisect means to cut in half. All right, and so if we go through and we talk about a couple, there's a couple theorems we want to talk about, okay, that I'll add in here for you. Okay, and that is the perpendicular bisector theorem. Bisector theorem. Okay. And what that says is if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Alright, so what the heck does that mean? Well, this is what it means. Is let's say we have a segment. Okay, we'll call it like this. Just some segment right there. Okay, and if there's a point on the perpendicular bisector, well, what's a perpendicular bisector? Well, first of all, a bisector means that we would have a line that splits this in half. So if that's in half, that means this is equal to this. Okay, and if it's a perpendicular bisector, that means it splits it in such a way that it creates a right angle right there. Okay, so this is if I label all this, call this A, B, C, and D. So AB is a perpendicular bisector of DC. Okay, well what this theorem right here is saying is if a point is on the perpendicular bisector, so let's just say there's a point, I don't know, right here. We'll call that E. If there's a point on the perpendicular bisector, then it is equidistant, so equally distant from the endpoints. That means this distance would be the same as this distance. So those distances would be the same. Okay, I'll indicate that by the double. And it doesn't matter where I put it. Let's say I put a point way down here. We'll call it F. As long as it's on the perpendicular bisector, that means this distance is the same as this distance. You can put another point up here, G. Distance is the same as this distance. Okay, that's perpendicular bisector theorem. Okay, and then the converse of the perpendicular bisector theorem says exactly, let me move this a little bit. Okay, says exactly the opposite. Okay, meaning converse of the perpendicular bisector, oops, not his bisector theorem. And that basically says if a point is equidistant, okay, from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Let me make that a little bit bigger. Okay. All right, which hopefully that makes sense. Basically, that simply says if I have a point, let's say it's G, okay, and I know the distance from G right here is the same from here to here, then that means this line right here has to be perpendicular. So it's just the exact opposite. Okay? All right. Let's see. Let's talk about a few other things here. Let's see. Let's talk about angle bisector theorem. All right. So let's do another one here for a second. Lots of writing in geometry in terms of, especially for this first couple sections we're going to talk about, which you need to write down. Theorem. All right. And so let me write it, and then I'll give you an example. If a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. Alright, so what the heck does that mean? Alright, well, here's what it means. Let's say we have an angle. We'll just draw a pretty simple one here. Okay, so we'll label this, the vertex right here, we'll call this A. We'll say it goes through point B and point C. Okay, and it says if a point is on the bisector of an angle, so that means this angle is getting split. So that means there's this. Okay, we'll call this D. Alright, so that means AD, this thing AD, is splitting AB or BAC. Okay, and so we would indicate that by, this is the way you indicate angles are the same. Okay, and so what that is saying is that if a point is on the bisector of an angle, then the point is equidistant to the side. So that means that if I were to, let's just say I pick another point, let's say we'll call it E. E is on the bisector. So therefore the distance, now this is important, when you measure distance from a point to a line, you measure it perpendicularly. So in other words, when I draw this is always going to be, when we're talking about distance, it's always going to be at a right angle. That right there is going to be the exact same distance as that part right there. Those two distances, we'll call this F, we'll call that G. So that means EG will be the same distance as EF. That's what that theorem right there is saying. And then we also have the converse. Now you'll notice that the converses, shocker, aren't going to be anything much more than just the exact opposite. Converse of the angle bisector theorem. And that says exactly what you probably think, and that is if a point is, in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector. Okay, and again, hopefully that makes some sense to you. All right, so what does that mean? So let's do, how about we do, how about we just keep, we're going to march on a little bit here right now, okay? We're going to get to the last part, okay? And then that's why we have our homework in class. We can actually work on some of those things, okay? All right, so last topic. So some of the last topics we're going to talk about are concurrent lines, medians, and altitudes. So let's just talk about concurrent here for a second. So concurrent means when you have three or more lines that intersect in one point. So for instance, I'm just going to draw three crazy, I don't want to do that. How do I get rid of that? There we go. Alright, so let's say I have three lines. 1, 2, and 3. We'll pretend those are straight. Anyways, so those are concurrent because they intersect in exactly one point. They intersect right there. And that point where they intersect, right there, this is called its point of concurrency. Okay, and that's important because that's what we're going to talk about here for a little while, is this idea of concurrency. And in triangles, there's some significant theorems that go along with that. Okay, so let's start with that. So here's a theorem that we want to start talking about. It doesn't have a special name to it or anything like that. Oops, I actually spelled theorem wrong. There we go. It says the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Alright, so that's a lot of stuff in there. So let's talk about this. So let's say we have a triangle. We'll just go something pretty simple here. Okay, and we'll just, for lack of better letters, we'll just say ABC. It says a perpendicular bisector of the sides of the triangle. So let's see if I can draw this fairly well. So perpendicular bisectors. So that means you have one coming up this way. Okay, so that is supposed to be perpendicular and it's supposed to bisect. You have another one coming from this direction. Again, we'll hope that my drawing will be good. So, perpendicular bisector, and then you'll have one more coming from over here. Okay, so we have 3 perpendicular bisectors, and you'll notice that they, even with my sketchy hand drawing right there, they all are concurrent at one point. And this theorem says that they meet or are concurrent at a point that's equidistant from the vertices, meaning that if I were to take the measurement, let's call this point right here, we'll call that E. And what it's saying is the distance from E to C is the same distance as it is from E to B as it is from E to A. So that's saying that EA is the same distance as EB. It's the same distance as EC. Okay, and that's the theorem. Okay. So another theorem we're going to talk about says that the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. So again, let's just draw another triangle. Draw a nice blue one this time. Again, I'll call this ABC. Okay, and this says the bisectors of the angles of a triangle. So let's see how good my drawing is again. Okay, there's one. These are congruent. Let's try this one. Ooh, that's not quite as good. Let's see if I can do better than that. Actually, let's see if I can do this. There we go. And let me try this again here. Okay, not the best I've ever done right there. And then another one. Yikes. Those are not the best in the world, no doubt. But what this is saying is that this point right here is equidistant, okay, to all the sides. So if I take this point, and we'll call that point D, just for argument's sake, if I were to figure out the distance, this distance, because remember a distance to a side has to be perpendicular, it's the same as this distance here, and it's the same as this distance here. So if I name those, let's say that's this point E, F, and G. And so this is saying that DE would be the same as DF, would be the same as DG. That's what that was saying. Okay, so there's lots of stuff going on here so far. All right, and there's lots of things that you should be writing down. So let's just kind of keep that trend going. So we're almost done. So a couple more definitions for you. So another definition is circumcenter of the triangle. So the point of concurrency of the perpendicular bisectors of a triangle. So remember a while back we did that. I drew a picture of a triangle. Okay, and then we drew all the perpendicular bisectors. So again, if I just draw real quickly, let's say that's perpendicular, pretend that bisects. Say we have another one, perpendicular, bisects, and then another one, perpendicular, and it bisects. So it's talking about this point right there. That point is called the circumcenter of the triangle. Okay? Alright, so two other quick definitions. Alright? And so one of those definitions, well, we'll do them both right now. Okay, and that is the median, okay, of a triangle, okay, which that is a segment, okay, whose endpoints are a vertex and the midpoint of the opposite side. Okay, and then we'll talk about the altitude. Altitude. Okay, and this is the perpendicular segment from a vertex to the line containing the opposite side. Now that sounds kind of funny, but I'll explain why it says it like that here in just a second. So for instance, I'll give you a couple examples here. So again, let's say we have a triangle. We'll do median first here. So median, all that is it starts at a vertex. Okay, so let's say if we call this A, B, C. Say it starts at A, and it just goes through and it splits the other side in half. Okay, say this point where it splits is called D. That means AD would be a median. That's it. It doesn't do it at a right angle or anything like that, but a median just simply is a segment. Okay, I drew it as a ray, but a segment whose endpoints are the vertex and the midpoint of the opposite side. Now an altitude is a little different. So let's say I have a nice simple triangle. Okay, and an altitude, call this ABC over here, goes from a vertex and is perpendicular to the opposite side. Now it says perpendicular to the line containing the opposite side. The reason why that says it is this. An altitude is simply, let's do a kind of a funky looking triangle. Call this D, E, F. So let's say we start at this vertex and go this way. That's easy, because then I can just simply go, alright, here goes my altitude, right angle. But the problem is, what if I go D? Can you draw a segment that goes like this that's perpendicular? No. And so that's why this part says the line containing the opposite side. And so the altitude from D would actually do this. It actually would drop down. You would extend this side right here, and the altitude would actually do this. Drop down. And that would be the altitude. Okay? And so that's why this part says the perpendicular segment from a vertex to the line containing the opposite side. Now here's a question for you. Let's see if we can come up with this. What if I have a segment that is a median and an altitude? What do you call that? Well, you would call that a perpendicular bisector, is what you would call that. Okay? Alright, lots of stuff to write down. We got lots of practice next time we see each other, but that's it for now. Alright, take care.